Today we shall be considering the topic simple AC circuits, simple alternating current circuit. At the end of these lectures, viewers would be able to define the term AC circuits, solve problems on peak voltage and peak current, define terms like capacitive reactance and inductive reactance, and also solve problems on capacitive and inductive reactance. Let's get started. What is AC circuit? AC circuits are circuits in which alternating current flows. Circuits in which alternating current flows. And alternating currents are currents that flow in both directions. They are used in power transmissions, electronic devices such as radio and television, computer technology, and telecommunication. Alternating currents are produced by time-dependent alternating voltages, which is in a sinusoidal form. The expression is written below. So equation 1, 2, 3 represents equation for alternating current in terms of EMF, potential difference, and current, where F is the frequency, angular velocity is omega by symbol, and omega t first angle, then V is alternating voltage, V naught is peak voltage, I instantaneous current, I naught is peak current. So E naught would be peak EMF. That one has not been written here. And then you see the symbol for omega. This symbol here, omega, is being replaced by 2 pi f. Omega equals to 2 pi f. So in place of omega, we had to replace. So all these ones are the same. For E, for EMF, we have peak EMF sine omega t. In place of omega, we put 2 pi f. Here we have peak voltage sine omega t. In place of omega, we put 2 pi f and all of that, but it's still the same thing. Let's move forward. This example says, given that V equals to 4 sine 800 pi t, estimate the amplitude, frequency, period of the wave, and angular velocity in radians per second. Looking at that expression, it is similar to equation 2. Equation 2, where we had V equals to V naught sine 2 pi ft. Let me go back so that we can see it clearly. Look at equation 2. That's the expression we are going to use in solving that problem. So we are going to compare equation 2 with the given expression here. So we now have V equals to 4 sine 800 pi t, the given expression, and then we compare equation 2, V equals to V naught sine 2 pi ft. By comparison, you can see that let me work on this pen. I'm coming. Okay, so we can see that this and this are common. So this will strike this. This, of course, will strike this. What do we have here? V0 equals to 4. So we are going to compare this one and this one. That's what I wanted to explain. So if we compare equation 2 with the given equation, we will see that our amplitude, our peak voltage is 4. And we are also going to compare for II to deduce the frequency, period, and angular velocity. So I now move down. I equals to 4 volts. That one doesn't require calculation. It's just a matter of comparison. Assuming the given equation was V equals to 5 sine 800 pi t, then our peak voltage or amplitude would have been V0 equals to 5. Is that clear? Okay, so V0 equals to 4V. We now compare equation 2 with the given expression 2 pi ft equals to 800 pi t. We cancel out the common terms. After cancelling out the common term, we will have 2f equals to 8. Look at t here. T is also here. Since we have t here, this t will cancel this other t, and pi will cancel pi. So what is left is 2f. 2f equals to 800, which is what we have written below. Dividing through by the coefficient of f, which is 2, we will have 400 hertz or per second. Okay, so we have gotten the frequency. Remember, period t equals to 1 over f. So when we substitute the value of f into the period, we have 1 over 400 s. So that's the solution, the value for the period. Angular velocity, remember I made mention that angular velocity, omega, equals to 2 pi f. So we have frequency to be 400, and we have pi here and 2. So we'll multiply 2 times pi times 400. That will give us 800 pi. Okay, so look at the expression. 800 pi radians per second. So we have successfully solved the example here. Let's go to the next example. The root mean square current. The root mean square current. The root mean square current is that steady current which will dissipate the same quantity of heat in a given resistor. That steady current that will dissipate the same quantity of heat at the same time in a given resistor. It is given by the expression I root mean square equals to I naught over root 2. So I had to combine two equations. That equation 4 you are seeing, I root mean square is equal to I naught all over root 2. We can as well say that I root mean square is equal to 0.7071 I naught. How did we get this? When you divide 1 over root 2, it gives you this value. So if we don't write it as the first one here, we write it as the second one. It still means the same thing. We can as well do the same thing to potential difference. So the same expression in equation 4 can be written in terms of potential difference. The mean square current can be measured using moving iron and hot wire meter. One could say, what instrument can be used to measure the mean square current? The mean square current can be measured with either the moving iron or the hot wire meter. Please take note of that. Let's move forward. The voltmeter and ammeter that we use at the lab could be used to measure root mean square voltages and current. So voltmeter and ammeter connected in a circuit reads the root mean square values of voltages and current. Remember from Ohm's law that V equals to IR. That's how we got equation 5. So when both current and voltage are in phase, current and voltage, when they travel together in step, they have the same frequency, amplitude, and wavelength, then one could say that they travel in phase. And when they travel in phase, we have V equals to IR. So V represents the root mean square voltage, I represents root mean square current, and the value of the resistor is R, or the resistance. We can as well do the same thing for peak voltage and peak current using this same expression, but below, instead of using root mean square, we use I naught. Here, we can replace this as V naught and I naught. Example 2. A voltmeter in an AC circuit usually reads the root mean square value of voltage. So this voltage is 240 volts and is the root mean square value of voltage. The question here says estimate the peak voltage or amplitude. You can call it either peak voltage or amplitude. I have already said something about that expression. V root mean square equals to V naught over root 2. So we are going to use that expression, and then we make the peak voltage the subject. So when we make the peak voltage the subject, we will have V naught equals to root 2 times V root mean square. Don't forget how we got this expression. Remember that V root mean square equals to V naught all over root 2. When we cross multiply, we will have us to V root mean square root 2. Alright, so that's how we obtain this value. When you substitute the value of root mean square V, which is 240, then you get the peak voltage. The solution is below. I don't intend to simplify it further than this, but if you like, you can do it and check the final value. When current and voltage reach their maximum values at the same time, they are said to be in phase. When current and voltage reach their maximum value at the same time, they are said to be in phase. Equation 2 can be substituted into equation 5 to obtain equation 6. What was equation 2? Equation 2 said I root mean square equals to V all over R. If we are making I the subject from the Ohm's law equation, and since V equals to V naught sine 2 pi ft, we have to substitute that value into this expression. So when we do that, we will get V naught sine 2 pi ft, which is what we have written here in this equation. Okay. The average power dissipated in a resistor is given by P average equals to I square R. Please note that expression because we are going to apply it. Look at this diagram. When a resistor or when a capacitor is connected in a circuit as shown in the diagram below. Look at this. We discover that current leads voltage by 90 degrees. In this circuit as well, if I'm considering the inductive circuit, when an inductor is connected across a potential difference as shown in the diagram here, voltage leads current by 90 degrees. You can say voltage leads current by 90 degrees, or current lags behind voltage by 90 degrees, or voltage leads current by a value of 1/4 cycle. For that of a capacitor, if potential difference is connected across a single capacitor as what we have seen in the figure here, current leads voltage by 90 degrees. And for us to recall this statement, we will use the word we are seeing here, Eli the Iceman. Eli the Iceman. Let me look at it here. Eli. So E here represents voltage. Voltage leads current. So in a circuit, an inductive circuit, voltage leads current, while in a capacitive circuit, current leads voltage. So the L here, you're seeing here, represents induction. Eli, voltage, E for voltage, L for inductor, and I for current. The Iceman. Current leads voltage in a capacitive connection. In this case, C here represents capacitor, and I is current, E is EMF. Looking at the circuit, the diagram, you can see the diagram where voltage leads current. you see that the voltage is ahead of current. And for the capacitive circuit, current leads voltage. And you see that the current is ahead of voltage. So when the current is maximum, voltage is 0. When voltage is maximum, current is at 0. The same thing here if you come to the inductive circuit. When the voltage is maximum, current is 0. And when voltage is 0, current is maximum, and vice versa. Let me check other additional information for this statement. Okay, if you look at the statement here, it says for a circuit with capacitor, current leads voltage. We have mentioned that. While voltage lags behind current, it's still the same statement. So one could say current leads voltage, or voltage lags behind current. That is for a capacitive circuit. The first angle is 90 degrees, or pi over 2 radians, or 1 over 2 cycles. So one could say in a capacitive circuit that current leads voltage by 90 degrees, or current leads voltage by pi over 2, or current leads voltage by 1 over 2 cycles. Or one can as well say that voltage lags behind current by 90 degrees, or voltage lags behind current by pi over 2, or voltage lags behind current by 1 over 2 cycles. And we can as well write it mathematically as V equals to V naught sine omega t. Then, since current leads voltage, you will now add pi over 2 in this expression. Okay, so you see my pointer. Let's scroll down. For a circuit with an inductor, current lags behind voltage in the circuit by pi over 2, or 90 degrees, or 1 over 2 cycles. And since current lags behind voltage, one could say that voltage leads current by pi over 2, or 90 degrees, or by 1 over 2 cycles. So please, I don't want you to be confused. And now look at the expression for the inductive circuit. For I equals to I naught sine omega t minus pi over 2. But for the other one, it was plus pi over 2. Okay, so that's the additional information I needed to show to you. The circuit with resistor, current and voltage are both in phase with each other. Circuit with resistor, current and voltage are both in phase with each other. Look at this circuit. This is a resistor connected across this potential difference. In this kind of circuit, look at the diagram. If you look at the diagram, you see that the diagram for the current and voltage, the one on top here is voltage, and the one below is current. This is V, this is I. They are both in phase. So you now see when current is maximum, when voltage is maximum, current is maximum. When voltage is zero, current is zero. When voltage is minimum, current is minimum. In this kind of plot, the waves are traveling in phase. So this occurs when a resistor is connected across potential difference. But in the other case that we explained, when an inductor is connected across potential difference, you see that voltage leads current. But when a capacitor is connected across, you see that current leads voltage. But if you connect a resistor, as shown in this diagram, current and voltage will always travel in step. They will always be in phase with each other. The capacitor opposes the flow of current. The opposition to the flow of alternating current as offered by a capacitor is known as capacitive reactance. Look at the symbol Xc. When you connect a capacitor in a circuit such that it opposes the flow of current, the opposition to the flow of electric current or alternating current as offered by a capacitor is referred to as capacitive reactance. If I use an inductor to connect in a circuit, the opposition offered to that alternating current as a result of the inductor being connected is referred to as inductive reactance. So whenever we talk about reactance, reactance has to do with opposition to the flow of current. Then capacitive reactance is the opposition to the flow of alternating current offered by a capacitor. Inductive reactance is the opposition to the flow of alternating current offered by an inductor. So for a capacitive reactance, we use the symbol Xc. Xc, look at it here. Inductive reactance would be XL. Take note of that. And they have their expression. Look at equation 7. Xc equals to 1 over 2 pi Fc. So the C there represents the value for the capacitor. Capacitor is measured in ohms. Capacitance is measured in ohms. F is frequency. Pi is a constant. So if a question is asked, explain the term capacitive reactance. What is capacitive reactance? simply the opposition to the flow of alternating current as offered by a capacitor. The SI unit of reactance is ohms. The SI unit of reactance is ohms. Applying voltage of frequency to capacitance C, we have V equals to IXC. Recall that from Ohm's law, we have V equals to IR. From Ohm's law, V equals to IR. But we eliminate R and then introduce IXC for that of capacitor. So that's how we get equation 8. Let's look at value for inductor or inductive reactance. This one says the opposition to the flow of alternating current as offered by an inductor. I've already said that is referred to as inductive reactance. So look at this value, the symbol XL. Inductive reactance is given by the expression XL equals to 2 pi FL, equation 9. So equation 7 and equation 9 are two different things. If we are applying voltage or frequency to the capacitance, we obtain equation 10. Please take note of these expressions because we are going to apply them. Okay. The next example. This expression says a 2 microfarad capacitor is connected directly across a 150 volt root mean square 60 Hz AC source. Find the root mean square value of current and the peak value of current. Looking at the given expression, you see that the equation comes with the value for the capacitance, which is 2 microfarad, and then the root mean square value of voltage to be 150 volts, and the frequency is 60 Hz. Remember, I used to say that the SI unit in physics is a language. It tells you what the quantity is. So we are to estimate the root mean square value of current and the peak value of current. We are going to use the expression for root mean square value of current, I, equals to V root mean square all over XC. And then we are also going to use peak current at the values. Now, we are going to find the capacitive reactance in this. That would be the first thing. And from there, we now use this expression because we already have the root mean square voltage. So for the second one, B, we now use I naught equals to I root mean square root 2. Let's move forward. Okay, so capacitive reactance XC equals to 1 over 2 pi FC. F is the frequency, C is the value for the capacitor. The symbol micro you are seeing here, this micro here represents 10 to power minus 6. Just trying to see how I can handle this pen. Clean this. Okay, so 10 to the power minus 6. Let me indicate so that you can see very well. This place here, this symbol means 10 to the power minus 6. Look at it here. If somebody says kilo, kilo means 10 to the power 3. Pico, giga, those are terms. So in this case, this is micro 10 to the power minus 6. So you have to multiply these 2 by 10 to the power minus 6. When you do the simplification, you get this value 1324.4 ohms. Now, we have the inductive reactance, we have potential difference, and we are going to make I the subject. Okay, so we now substitute the value for the root mean square voltage, which is 150 in the equation. Look at it here. Root mean square voltage here. Substitute, and then we use this 0.113. Then for the peak voltage, we apply the expression I have written by the side here. When you substitute the value for I, root mean square current that we get here, you get 0.160 ampere. I would like you to do this example, or should I call it assignment. Look at it here. It's still the same as example 3, but in this case, this one is in